Section 34, Interpreting Differential Equations and Euler's Method. In this section, you will not be forced to solve differential equations. You will be forced to use differential equations to solve problems. So we have some example problems in this section. In addition, these are really similar to the AP free response problems. So the AP free response problems always have a differential equation question, always one, and then sometimes more than one. And in either of those, you will have to do this particular skill, which is making tangent lines based off of differential equations, estimating points, that sort of thing. So, first thing, what is a differential equation? It's just an equation for the slope of a line. A lot of times we know the relationship between things, like for example, Newton's law of cooling. We know, whoops, not Y, temperature. We know that the change in temperature is proportional to the difference between the current temperature and the temperature at the beginning, or that it's going towards, so like the room temperature. So the rate at which a coffee cup cools down slows down as it goes along because this difference, the difference between the current temperature and the room temperature in the room, gets smaller and smaller. And so like if you have a cup of coffee that's 80 degrees and you're in an 80-degree room, your cup of coffee won't cool down at all because you're in an 80-degree room. But if you have your actually hot cup of coffee, which is, 140 degrees or something, even in an 80-degree room, it's going to cool down. However, if you went into a 20-degree room and this difference was 120, it would be cooling way faster. So it's understanding what this is. This is the rate of change, and using this helps us solve a bunch of problems. So our first question is that this is actually really similar to a free response question from a few years ago. There's a function which relates the rate at which a shoreline of a beachfront property is changing. And they give us the equation. And they say, when will the shoreline of the beach stop receding? So when it stops receding is when its equation switches from positive to negative. Because as long as it's positive, it's receding. Because this is measuring the rate of receding. And so we just need to figure out where 8 minus 0.6t is equal to 0. So we just add 0.6t to the other side, and we get 8 equals 0.6t, and we divide by 0.6, and t equals 8 over 0.6, which is 13 2/3, which is the answer I showed there. So sometimes these are really easy. Like, when does this thing change? It's just converting words into how does this apply to math. We also have Eulers Method in this section. Eulers Method, remember, is, say we have some function that we're using Eulers Method on, and the function looks like this. But since we're using Eulers Method, all we know is its derivative. So say this is y is equal to x minus y, or y prime is equal to x minus y. It means at every point, we're going to sit at this point, we're going to go, okay, this guy's tangent line goes to the, it looks like that. It's about that flat. And I'm going to use that to estimate my next point. And then I'm going to go to my next point and use this value, plug it into my differential equation, and go up and estimate the next point by estimating the slope there. And then use that to estimate the next point. And what we end up with is an approximation of the graph we're trying to build. And we do this when we can't solve the differential equation. You might remember how I solved this in class or not. It doesn't matter when you're doing Eulers because you're just proving, you're using this method to approximate. So let's try a few problems. Oh, there's an Eulers over approximation there. Okay, so first question. We're given a differential equation, negative x over y. It's a circle. And we're given a starting value. We're trying to find the equation for the tangent line of y at x equals 13. So First deal is x equals 13, y equals 25, because we're given this point. So we just plug it into our equation. dy over dx is equal to negative 13 over 25. And now we have the slope. So we're going to have y minus y1 is equal to slope times x minus x1. And that's it. So I love using point slope because it makes these problems so easy. Yeah, this is point slope form. I just plugged in stuff for x1, y1, and m. Okay, so that's half of that problem. The other problem we have here has us do Eulers Method. So remember, our starting point with Eulers Method is we're generally given the starting point, and we're trying to estimate onto the next point. So we have two intervals of n. We're estimating y of 15. So we're going to go from y of 13, which is 25, to y of 14 after we solve it, which is, we don't know, to y of 15, which is where we want to actually get, which, down here. So let's do the intermediate steps. First thing we do is we find the slope at 13. The slope at 13 is, well, it says it's the same equation as over here, so we're just going to use that equation. It's negative 13 over 15, we knew that. Or 13 over 25. So y of 14 is going to be our old y value, our previous one, plus our slope, negative 13 over 25, times how far we're moving over. In this case, just 1. Because I said estimate y of 15 using two intervals of n, so each one is 1 wide. And so our next point is just going to be 24 and 12 25ths, because that's what 25 minus 13 25ths is. All right, so now we need to find, I did not give myself enough room here. We need to find y prime of 14 to estimate our next point. And so it's negative x over y, so it's going to be negative 14 over 24 and 12 25ths. Now you might notice the math is going to get pretty terrible here, but that's okay, because we're just estimating y of 15, which is our previous value plus our slope times 1. And you can just leave your answer like this. That's our estimation. You do not need to simplify beyond what is here, which is our starting value times our slope times the interval width. And that's it.